Hello, everybody, and welcome back to Math 100. Today, we are going to talk about music, more specifically, music and mathematics. So this is section 7.3, and we'll talk about one magical number which sort of governs our entire system of music. All right, let's get started on section 7.3. So section 7.3 is all about music and mathematics. Like music and like art and mathematics, sometimes what is creative and aesthetic seem to have nothing to do with mathematics, but it turns out mathematics is highly artistic. And because art is partly governed by patterns and things like the beauty, it makes sense that mathematics has a lot to say about and forms some foundational elements of mathematics, music, and art. All right. So this goes all the way back to about almost 2,500 years ago. There was a man by the name of Pythagoras. He's pretty famous, Pythagoras, not for anything musical. I mean, he actually is, but most people know him as a mathematician and philosopher, and he was all of those. Okay, a Greek mathematician. He also studied ratios, and he used to say that ratios provide harmony, which provide beauty, which basically means ratios are beautiful, and the world's beauty come from ratios of numbers. So fractions, for instance, and we'll talk about how that thought introduced him to musical harmony in the next few minutes. But he is sometimes considered the father of music theory because he seems to be the first, maybe, to establish a formal system of music. All right, and then we go to the Middle Age, right before the Renaissance, in what is today considered Europe. They started to make universities in Spain, in Italy, and in other places. And they had a curriculum consisting of 4 topics or 4 disciplines. And that is known as quadrivium. Okay, quad, of course, means 4. And the quadrivium is the 4-subject curriculum in higher education in medieval universities, such as ones in Bologna and other places, including arithmetic, geometry, astronomy, and music. And they all, if you can look at it, they all have to do with mathematics. Okay, clearly arithmetic is a part of mathematics. Quite useful. Geometry was really a fundamental aspect of mathematics ever since the time of the Greeks. And then astronomy, using lots of mathematics to calculate the movement of stars and other heavenly bodies. Music, as you will see, is heavily governed by mathematics. All right, so speaking of music, let's talk about sound. What is sound? Sound is produced by air vibration. If there's no air, there is no sound, right? And how high that note is or sound is, it's called the pitch, right? Some of you may even have perfect pitch, which means you can tell exactly what note the sound is. And so pitch is determined by frequency of that sound or the air vibration. That is how many times the string or air or whatever is vibrating per second, okay? And so that frequency of the vibration determines how high the sound is. And in our voice, of course, this is determined by our muscle called the vocal cord, right? So if I can talk like this, it's very, very low. Oh, if I can speak like this, it's very high pitch. And what's changing is the vibration, the air vibration frequency. All right, I have a little portion of a keyboard. And you don't have to know a lot. And some of you already know this as something very basic. Some of you are probably performing music, and some of you may have been studying music theory for years, whereas others of you may never see anything like this. 5 lines called the staff, and this is called the treble clef, and you have what is known as the an octave here, and this is a C major scale, the C major scale. All right, so you don't need to know a lot of musical or music theory, but what I'm going to tell you about is basically the simple patterns or the simple elements of music that are governed by or informed by mathematics. Okay. All right. So I have 8 notes here: C, D, E, F, G, and then A, B, C. This is the traditional. These are the traditional names given to the 7 notes. You know, it's A through G, and then of course you see C twice at the beginning and at the end, and that's because you have an octave here. An oct means 8, right? An octave is the interval meaning from here to here, right? Okay, so maybe I should rank here. It's from here to here. So this interval consists of these keys, both black and white. And if you play all the white keys here, that would be the C major scale, which is what you see here. All right, but anyway, an octave is the interval of musical sound, which in which the frequency doubles. Okay, so the frequency doubles from this C, oops, wrong way, from this C to this C. Okay, and then you have another C, well, right here, and then this is another C, and then the frequency doubles again here. Okay, so times two, of course, the frequency then quadruples from this C to this C, right? I will have more to say about this. Okay, what you see here is a scale. All right, a scale is the frequency. I'm sorry, a scale is the sequence, or maybe I should say, you know what? It's probably better to change this to A, because there are many different scales. So a scale is a sequence of musical tones spanning, and again, the same word, an octave. Like I said, if you have studied music, or if you have been a student of music for a long time, you know this is the C major scale. There's a C minor scale and the D major scale and D minor scales, and that would involve some of these flats and sharps, the black keys. We will not get into it, but basically all the scales look like this. A scale is a sequence of musical tones spanning an octave. Most scales have 12 tones. Wait a minute, I only have 8 here, right? That's an octave, OCT representing 8. But if you include these black keys, they define what is called half notes. And so altogether in an octave, you have 12 tones plus the last one, which is really belongs to the next scale, where the next scale begins. All right, most scales have 12 tones with a frequency increasing with a common ratio. All right, so here's what I'm talking about, or percentage. Okay, here's what I'm talking about. All right, so this is the C. Okay, let's say this is called the middle C. All right, and then this is called C sharp. This is D. This is D sharp, and this is E. And there is no E sharp. Well, I mean, technically, maybe there is if you don't have tempered scale. But the next key is called F. Okay, and then you have F sharp, G, G sharp, A sharp, sometimes called B flat, and then this is A, this is B, and then there is no B sharp. If there's B sharp in our tempered scale, it's called C. And so that's all together from this C to this B. That's 12 notes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And so each of these is separated by what we call half tones or half steps. And each of these, when you go from C to C sharp and then C sharp to D, D to D sharp, D sharp to E, E to F, every time there the frequency increases with a pay close attention here, with a common ratio. So the frequency does not grow linearly. Remember in chapter 5, the frequency grows with a common ratio, and therefore what kind of growth is this? It's not linear growth. It's the other one. Yeah, it's the exponential growth, right? So we have seen that a couple of times already, right? Exponential growth was first introduced in chapter 3. Yeah, financial calculation, compound interest. All right. So the mathematics for music is pretty much the same as that mathematics for compound interest. I know it sounds strange that money and music have something in common, but they do. Okay. The underlying mathematical structure is the same for compound interest with a common ratio, where we call that the annual percentage rate, APR. We are going to find this ratio. Okay, that allows us to double our frequency every time we go 12 half steps. Okay, so like money and population, this is doubling every octave. So every 12 half steps, or every 12 times or periods, compounding periods, this thing doubles, or frequency doubles, just like money doubled, every so many years under exponential growth or compound interest. All right, so we talk about the different types of tuning. Typical one is called the A tuning. What in the world is the A tuning? Okay, in the old days, when I was a kid, and you may have seen this, there was this thing that's made of steel called a tuning fork, okay? And you hit this tuning fork on a wall, or with your fist, or with a special stick or something, hit it, and then it makes the vibration. It's, of course, it starts to make the sound, and that is A. And A has 440 cycles per second. Sometimes it's called hertz. Okay, that's the same thing, cycles per second, and the hertz both means that how many times the air vibrates when you hit this note, right? So this was a typical thing. I used to have one of these tuning forks when I used to be into playing guitars, and this is how we tuned. Now, of course, we have all kinds of electronic gadgets, and you don't need this anymore. In fact, I have an app on my phone that is an electronic tuner. How convenient, right? Okay, people like me who don't have perfect pitch have to depend on tuning forks, or some kind of a tuner. All right, the A tuning is the tuning whereby you set the middle A to 440. Okay, and so CPS, as I said, stands for cycles per second. Okay, and this is also the same as the unit hertz. Okay, HZ is the abbreviation for it. All right, we'll talk about the equation in just a minute. All right, but here's the maybe I should write this down. The A tuning is most common, I think. Okay, but here, let's try the C tuning with 260. Now, I will let you do your A tuning, I think, in your homework, or on your quiz or something like that, right? So there are different types of tunings, and A tuning is the one that starts at 440. That's most common. And I want you to figure this out on your, later on your assignment. But at this point, let's do what is considered a C tuning, where C, the middle C, is set to 260. Cycles per second. This is another sort of common way of doing this. Okay, now here's the math that is going to give us how to give us the information on how to fill out or fill in this form. All right, so here we go. All right, so it doesn't really matter where you start, but in my example here, let's say the C tuning starts with the initial value, the initial frequency of 260, right? And then what we have is, of course, to get the next one, we take the current frequency and multiply it by 1 plus R, where R is the ratio. Remember, we have this common ratio, and that's what we're trying to find out now. And then we raise it to the nth power, and no, that's not the case. All right, so you take the previous number, and then you multiply it by 1 plus R. This is, of course, R% more than P sub n, and that's how you get the next one, right? What we want is this. We want, okay, remember, C to, let's see, this to B, this is your 12 half steps. All right, C, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so after the 12 increases, next time we'll get C. This is your, so P naught is 260, and this will be P12 because this will the 12 half steps higher than the original C, and we want this to be double the frequency, which is 520, right? This is the defining characteristic of an octave. An octave, like from C to C, is the interval in which the frequency doubles. So if we start with 260, which is sort of a standard frequency for the C tuning, then you want the next high C to be exactly twice as much or twice in frequency. So we want P of 12 to be 520, right? All right, so this, by the way, this is a, what do we call this? The recursive definition, right? The recursive formula. But this turns out to be, maybe I should say, remember the formula for the compound interest. P sub n is going to be the initial value times 1 plus r to the nth power. And the reason is every time you go to the next step from C to C sharp, from C sharp to D and so on, we are going to multiply it by 1 plus r. So from here to here, multiply by 1 plus r. From here to here, multiply by 260 by 1 plus r twice. So it's 1 plus r squared. From here to here, this is multiply by multiply 260 by 1 plus r 3 times, or a cube, and so on. So this is that general formula, which we learned, back in chapter 6 for any kind of a exponential growth. And we also saw this in chapter 3 in terms of compound interest. So there's nothing new about this formula. But you want this, which is 260, 1 plus r, to the 12th power. You want this to be exactly 520. All right, so I'm going to divide by 260. You are, by the way, not responsible for remembering all this procedure. All we are trying to do now is to find that R, the rate, the percentage increase for each half step, so that we can fill in this form. And that number, of course, is the number that governs all our musical scales, right? So I don't think it'll be an exaggeration to say that the number that we are looking for right now, this R, which separates each half interval or half step, is really the one number that holds the key to all of the, the music, especially the Western music. All right, so 1 plus R to the 12th power is 2. Now, I got 2 because I divided 520 by 260 and you get 2. So if I can solve this equation, now this is the equation we need to solve to find that R. That would be great. This is not an algebra class we are in, and so I am not going to give you all the details here. But at this point, what we do is to take the 12th root. You don't need to know the details of this, but you take the 12th root of each side, and this is what you'll end up with. When you take the 12th root of 1 plus r to the 12th, you just get what's inside the parentheses, 1 plus r. And this side will be 2 to the 1/12th, or the 12th power, or the 12th root of 2. Okay, and there's this is a fixed number. You can even calculate this. You can enter this on your calculator. 2 raised to the, how do I do this? 2 raised to the power of 1 divided by 12. Okay, this will give you this number, and that turns out to be 1.05. Okay, hold on a second. Let me see. 59463, and so on. All right. Now, of course, this is 1 plus that. So R, the rate, the common ratio separating each half step, turns out to be 0.059463 ... which of course is equal to 5.946% approximately. What do we just find? I'm calling this the magic number that governs our music, right? And that's exactly that. So if you go from C to C sharp or C sharp to D or G to G sharp or G sharp to A, just go to the next step by multiplying the current frequency by 1.059463 to get to the next frequency. In other words, each time you go from one note to the next note, half step higher, we are adding 5.946% to the frequency. Okay, and the exponential growth is based on this percentage, which is fixed. Okay, so that is how we find this number, all these numbers here. So for this number, okay, so for C sharp, all we have to do is 260 times 1.059463. I enter this number in the memory of my calculator. That would make it easier. Or you can use a spreadsheet program like Excel to calculate this. Right. So if you do this calculation, you will see that this will be 27546. Okay, and then you multiply this by this element again, 1.059463, and then the next one will be 291.84. So if you do the C scale, or if you do the C tuning, the frequency of D would be 291.84 cycles per second. Right now, you don't want to keep, you can keep multiplying these numbers by 1.0594, but you could actually use this formula here. All right, so for this one, this is P3. So what I do is I take 260 times 1 plus this number, so in other words, it's 1.059463 raised to the third power. Okay, and that's going to give you the frequency of D sharp, and so on. All right, so I'm going to go ahead and just write down these numbers. You should go ahead and do this on your own by calculating, multiplying each of these by 1.059463 to get to the next number, or use this formula to calculate these frequencies. For F, which is P5, that's 34706. For F sharp, 3677, and then 389.56, that's the frequency of G when C is set to 260. G sharp is 412.72. Clearly, you don't have to memorize these numbers, but you should know where this is coming from. Right? A sharp 463.27, B 490.81. All right, and then C, this is exactly the double of 260, so there is nothing to calculate. C sharp is 550.92, and D, this is the D higher than 1 octave from where we started, and that's 583.7. Next time you get to C, it'll be 1040. Okay, because from here it doubles again, right? So this is how the musical scales are constructed in terms of their frequencies. Okay, so let me go ahead and write what I have been saying here, and because I think this will be a good summary for you to remember and keep in mind in terms of music. Okay, what am I going to say? So the frequency of each note in the musical scale grows exponentially with a common ratio, which is percentage, of what? 5.9463% for each half step. And we have to say it's half step because we are considering all the sharps, and that's how it works. In an octave, you have 12 half steps plus the note exactly 1 octave higher than what you started with. Okay, so this allows the frequency to double each octave. All right, so the magic number in this case is 5.9463%. This really indeed is the magic number in music, okay? And so every half step is separated by about 6%, or more precisely 5.946%. And so, so what we say is this: the doubling time. Now, of course, this is not time, but the doubling time, if this was in the context of a population growth or compound interest, is 12. Okay, so look, if your money is invested with 5.9463% compounded annually, after 12 years, your money will double, and after 24 years, it's going to quadruple, and so on. Okay, so the mathematics that let's say you are investing your money at 5.9463% annually. That math is going to be exactly the same as the math used to determine the frequencies of all of these notes, starting at any number, as long as it grows to its double in 12 steps. Okay, so yeah, cool, right? I mean, money and finance, there's something in common, and the underlying mathematical structure is the same. All right, so in the second segment, or the second half of this section, we'll be talking about harmony. We are going to use these frequencies to talk about chords and how sometimes you can harmonize, and sometimes two sounds clash, two pitches clash. Okay, so what's the secret for harmony? And that is in the next section. All right. Let's go to part 2.